In this video, we'll introduce another connective called the horseshoe, which is typically used in propositional logic to represent sentences of the form if P then Q. These are called conditional sentences. The same conditional relation can also be expressed with other equivalent sentences, such as Q if P or Q whenever P. A conditional sentence has two parts. Whatever is to the left of the horseshoe is called the antecedent, whereas what is after the horseshoe is the consequent. Like all propositional logic connectives, the horseshoe is completely defined by its truth table. Let's start with the first row, in which both P and Q are true. Which value should if P then Q have at that row? Well, if the antecedent is true and the consequent is true, then there is no reason to think that the conditional itself would be false. So let's assign the value true. Now it's really clear that the second row should be false. If the antecedent is true, but the consequent is false, then the conditional can't be true. Here's an illustration. Suppose the conditional sentence is, if I'm swimming, then I'm wet. The antecedent is am swimming. The consequent is I'm wet. Now, suppose that it is true that I'm swimming, but false that I'm wet. Then the statement that if I'm swimming, then I get wet is false, because it's possible for me to be swimming without at the same time being wet. The first two rows are the easy ones. The next two are more tricky. What should we say in the case in which the antecedent is false? Take again our conditional sentence, if I'm swimming, I'm wet. Now suppose that it's false that I'm swimming. Then what should we say about if I'm swimming, I'm wet? Is it true or is it false? One sensible response would be that without the antecedent being true, we really can't evaluate the statement. However, one of the main things about propositional logic is that every sentence must have one and only one truth value. That is, every sentence must be either true or false. We can't leave any of the cells empty. The convention in propositional logic is that whenever the antecedent is false, the whole conditional is going to be true. This might sound a little odd, but it works. And it does make sense. What we want to capture with the horseshoe is the kind of sentence that is going to be false when the antecedent is true and the consequent is false. If I tell you that if I'm swimming, then I'm wet, what I'm telling you is that whenever I'm swimming, I'm wet. That is that if I'm swimming, you can automatically tell that I'm wet. Or what comes to the same. What I'm saying is that it's never the case that I'm swimming and also that I'm not wet. So this is the final truth table for the horseshoe. A sentence of the form P horseshoe Q is only false if the antecedent is true and the consequent is false, and true in every other case. Now, the horseshoe is only an approximation to if-then sentences in English, but it's a useful one since it allows us to preserve certain patterns of reasoning, as we'll see in the next section. Just like we saw that there were some argument patterns that were valid or invalid because of the way in which the conjunction, the disjunction, and the negation behave, there are also arguments whose validity or invalidity, according to the case, depend on the meaning we've assigned to the conditional symbol, that is, the horseshoe. For instance, take a look at these two patterns. One of them is valid and the other is invalid. Can you determine which is which? If you want, you can stop the video to figure it out. So let's see the first pattern, which is if P then Q, P therefore Q. There's only one row where both premises are true, and that is the first row. And in that same row, the conclusion is true as well. So the argument has no counterexamples and is thus valid. This is indeed a very famous and common patterns of argument, which is usually called Modus Ponens, or also detaching the consequent. The second pattern does have a counterexample, though. Now the premises are if P then Q and Q, and the conclusion is P. So the second premise and the conclusion have switched places. There are two rows in which both premises are true, namely 1 and 3. In row 1, the conclusion is also true, so it's all right. In row 3, however, the conclusion is false. So that constitutes a counterexample. And that shows that it's possible for the premises to be true and the conclusion to be false. That is, this argument pattern is invalid. In fact, this pattern has been given a name. It is the fallacy of affirming the consequent. It is a fallacy in that it seems valid, but isn't. It seems valid because it's quite similar to Modus Ponens, the form what we just saw. If you definitely want to convince yourself that this form is invalid, just substitute P and Q with two actual sentences. So the argument would say, if I'm swimming, I'm wet. I'm wet, therefore I'm swimming. Line 3 is a counterexample. It is true that if I'm swimming, I'm wet, and also true that I'm wet. But it's false that I'm swimming, say because I am under the rain without an umbrella. Now, look at these two patterns. Are both of them valid? Again, if you want to check this on your own, then you can pause the video. So let's see the first form. It says, if P then Q, not P, therefore not Q. Here we have a column for not P, which is the second premise, as well as one for not Q, which is the conclusion. Is there any row in which the premises are all true and the conclusion false? If you pay attention to row number 3, you can see that both premises are true and that the conclusion is false. So we have a counterexample, which shows that the form is invalid. By the way, this invalid form is called denying the antecedent. Now it's your turn to check the other form. Here you have the truth table already done. And when you're done with the previous form, you can check the validity of this form. Notice that in this case you have 3 letters. So how many rows will your truth table have?